Hey folks, today we're going to talk about Graham's law. It's another one of the gas laws. What we want to do first is we want to talk about a couple of concepts. The first concept is something called diffusion. If you think of someone down the hall is making popcorn, that smell is going to diffuse into the atmosphere and it's going to come around. You're going to smell it if you walk down the hall. You're going to smell it, frankly, all over the building, right? If we had a skunk in one place, so you walk outside and you smell a skunk. Well, the reason you smell a skunk is because the air molecules outside are always moving, and they're always moving quickly. We've talked about this in a previous podcast. Those air molecules aren't sitting still, so even if you're out there at 6 in the morning where it's very, very calm and there's no wind, the air molecules are still moving and bouncing and whacking off of each other all the time. So what happens is you have a skunk that has a smell, and that smell is all concentrated in one area. Well, those smell particles all move, and they bounce off of each other, and the air molecules hit them and whack them and move them around. And so those smell particles diffuse, and they always go from an area of high concentration to an area of low concentration where they're spread out. And over time, they spread out more and more and more and more to the point where you can't smell them anymore. So that's true if you think of someone walking past you and they have perfume on. All right, you're going to smell that perfume when they walk by. But within a couple of minutes, that smell is going to dissipate. You're not going to smell it anymore. The same thing is true with smoke. Smoke, if it's near you, you're going to see it. But then over time, it's going to dissipate to the point where you don't see it anymore. That's the concept of diffusion. And the reason for this is gas molecules are moving. They're moving often at over 1,000 miles an hour. They bump each other, they hit each other, they bounce off each other, and those molecules all bounce the smells or whatever it is all over the place. Now you can see this easier in water. For example, if I take some water and I put one drop of food coloring in the water isn't jostling around, you don't see it, but really what's happening is those water molecules are constantly moving. And as a result, they move all of the food coloring, they start to spread it out to the point where eventually it becomes one just consistently green color throughout the whole liquid. And if you add more liquid, of course, it would spread out even more. Okay. So, diffusion, the concept is that smaller or lighter molecules move faster, where the larger and heavier molecules move slower, and it all has to do with kinetic energy. And the formula for kinetic energy, which I do not expect you to know or to memorize, is it's 1/2 mass times velocity. So even though you don't have to know that, let's think about that for a minute. If you have something that has a bigger mass, it's going to move slower. So it's 1/2 times your mass times your velocity squared. So as your mass gets bigger, your velocity gets smaller, and vice versa. Of course, your kinetic energy is temperature dependent. So as your temperature goes down and approaches absolute zero, kinetic energy goes to zero. Since your mass isn't going to zero, what has to happen is your velocity has to go to zero. So eventually when you hit absolute zero, your velocity ends up at zero, and molecules stop moving. All right, so we have this guy called Graham, Thomas Graham, and he came up with this law of effusion. Now, effusion and diffusion are very similar. You already know what diffusion is. Effusion is you have a box that has molecules in it. Let's say this box that's on the left. But as you get to the box that's over here on the right, you'll notice that over here you have a hole in it. And it's a very, very small hole, and it allows molecules to go through occasionally. Right? And so over time, they manage to just barely fit through that hole and come over into this big open area over here. That's called effusion. So, he said that the rate of gas effusion is inversely proportional, in other words, as one goes up, the other goes down, to the square root of the molar mass. Yeah, right. English? Really? Okay, let's see what we're talking about here. The concept is, let's say you have a screen, and you have a fly that's over here, and you have a little gnat that's over here. Which one's going to make it through the screen easier? Well, of course, the smaller thing. The smaller thing is the lighter thing. So as you're trying to get through this screen, the gnat can make it through and the fly can't make it through. Now eventually a fly is finally going to figure out a way to get through that screen. All right? And it will get through the screen or around the screen or whatever. The bottom line is the gnat can make it through a lot easier than the fly can make it through. The thing that's small, the thing that has very, very little mass can make it through, but the thing that has a lot of mass is not going to make it through the screen very easily. So we can actually derive Graham's law of diffusion from the law of kinetic energy. Kinetic energy says kinetic energy is 1/2 the mass times the velocity squared. So if we have two molecules, one of them that's very tiny and one of them that's very, very big, right? This one has very little mass. This one has a lot of mass. Let's call this A over here, and let's call this B over here. All right? Now, because they're both at the same temperature, their kinetic energy is the same. All right? They're both floating around in our atmosphere, in our air. Okay? One of them is, I don't know, let's say oxygen or hydrogen or helium. And the other one, that's A. And then B is the smell of a skunk or the smell of an orange or whatever, some smell. All right. But the kinetic energies are the same, so we have 1/2 times the mass of A times the velocity of A squared is equal to our kinetic energy. But since the kinetic energy of both molecules is the same, that's 1/2 times the mass of B times the velocity of B squared. Well, that means they're equal to each other. And we'll notice that we have 1/2 on both sides, so those can disappear. So we end up with the mass of A times the velocity of A squared is equal to the mass of B times the velocity of B squared. Well, let's say what we want to do now is we want to put the masses on one side and the velocities on the other. Well, if I take both sides and I divide by the mass of B, that will cancel out the masses of B. And let's say I divide both sides by the velocity of A squared. That'll cancel the velocities of A squared. So I'm left with the mass of A over the mass of B is equal to the velocity of B squared over the velocity of A squared. If I take the square roots of both sides, I get the square root of the molar mass of A divided by the square root of the molar mass of B is equal to the velocity of B divided by the velocity, or the rate, of A. Right? So I've actually gone and derived Graham's law of diffusion. Right? So Graham's law of diffusion, and you should write this down, is that the velocity or the rate of A divided by the velocity or the rate of B is equal to the square root of the inverse of those of the molar masses. Notice we have B over A over here. So we have A over B on the left and B over A on the right. Okay, so you should write that down. Pause the video. Good job. Okay, now how in the world do we use this? Well, if we have something where we're saying we know the molar mass of two substances, and we know how fast one is going, we should be able to calculate the other one. So let's go ahead and do that. All right. At 25 degrees Celsius, helium diffuses at 1,360 meters per second. That's like 4,000 feet per second. That's huge. That's really, really fast. Right? So that means a helium molecule is traveling like 4,000 feet per second. That would be like 40 football fields. Right? Well, of course, it's going to hit something before it goes 40 football fields, but it's going at that rate of speed. And that's helium, and it's asking us for how fast does carbon dioxide diffuse. Well, if we look up helium on the periodic table, we can find out that helium weighs 4.003 grams. And if we figure out CO2, that's carbon plus 2 oxygens, and that's going to be 44.009. I'm not going to waste your time doing that. You all know how to do that. 44.009 grams. So, if I now use Graham's law, let's go back and look at Graham's law. Hopefully you wrote it down. There it is. The rate of A divided by the rate of B equals the molar mass of B divided by the molar mass of A, the square roots of those. Well, we know the right-hand side. We know these. Right? And we know this. So let's, over here, so let's go ahead and put some numbers in. Right? We know that, that the rate of A, well, let's do the molar mass because we've got those. The square root of 4.003 divided by the square root of 44.009 equals, now we're going to flip these. Remember, this is helium, the top one, and the bottom one is CO2. So we're going to put CO2 on the top, which is the rate, or the speed, whatever you want to do, the rate of CO2, and the rate of helium on the bottom was 1,360 meters per second. So our answer up here is going to be in meters per second, and we simply do cross multiplication. So we do the square root of 4.003 times 1360. We do that divided by the square root of 44.009. And when we actually do the math, we come up with 410 meters per second. And that is the speed of carbon dioxide. So that just gives you an example of how to use Graham's law. It's kind of cool. Gives you an idea of how fast these molecules are really going. And 25 degrees Celsius is about room temperature. So it's pretty fast. All right, go ahead and try and do some of on your own. Right? If you have questions, please see us in class. We'll be happy to help you. Have a great day. Take care. Bye.